Hello everyone. We are here doing differential equations. This is like part 4, logistic growth. Logistic growth starts out as exponential growth, but then there's a limit, there's a limitation, there's some sort of thing that's putting a boundary on that upper growth of exponential. So we start off with a basic concept from simple exponential growth, and that is that the population over time is growing at a rate that is proportional to the population size. Larger population, larger growth. Smaller, smaller growth. Except that as the population grows, we're going to introduce this factor that will start to limit it based on a carrying capacity. It's going to be the population over that maximum allowed population. So for instance, in the beginning when the population is small, this fraction is close to 0, and so 1 minus 0 is just 1, and we have that same exact expression that we began with for simple exponential growth. But as the population gets larger, it starts to balance out with m. It comes closer to 1, 1 minus 1 is 0, and that shuts off any further growth. So just to picture it, it's a little direction field. Here's our baseline of 0. Here's our level m. And that is going to be sort of a horizontal boundary that any population is going to start off with a kind of a shallow slope. This is like our direction field. And then it's going to increase to a maximum growth halfway and then kind of flatten out again to be sort of shallow growth at the top until we get to that top. That's all coming from that fraction p over m. So I'm just going to sketch in a simple direction field like this, and in between would be like this, and in between that would be like that. So wherever you start, here or way down low, it's just going to grow exponentially but then start to flatten out. Okay, and it'll be symmetrical if we start close to 0 like this, always flattening out. If you start at almost 0, it might take a while, but then it'll get up there like that. Okay, so it's easy to sort of picture what's going on if you can think of it as a direction field like that. Well, it turns out this is a separable equation, so we can actually solve for it. Isn't that exciting? And I think this is a totally cool application of the simple ideas that come into differential equations and calculus in general. We can just express the concept, this simple proportional concept of growth, and then we can solve it and get a very, very useful equation. All right, so what do? Well, we separate this. So we're going to just write this as k over, and then p times 1 minus p over m, and that's to the minus 1. Same thing, that minus 1 and flip it up above, and that's what we started with. So then I can write the integral then as the integral of 1 over the minus 1 part, then p times 1 minus p over m dp, and that's going to be equal to the integral of k then with dt. That's the simple side. All right, well, I'm just going to, we know that this is going to be equal to just kx, or kt rather. T is our variable. I'm going to leave that aside for now and really work on this side. Oh, plus c. Let's remember that we're going to put our constant on the side over here with the t. Well, what happens over here is if we think of this 1 as being m over m, so I'm just going to sneak that in right now, m over m. Then I've got the common denominator, so this will be just then the integral of 1 over p times m minus p over that common denominator 1 dp. Well, that's just going to be, now I've got a fraction down below and it's inverted, so I can flip it around. That's going to be the integral then of m over then p times m minus p, okay, dp. Well, what is this going to be equal to? To integrate this most easily, I'm going to separate this into partial fractions. So that is going to be then just this p part, some mystery amount a over p, plus then another mystery amount b over m minus p. All right, so if you wanted to, you could pause the camera and you could go through and solve this, practice your partial fraction skills. I'm going to cheat like they do in the cooking shows. And I'm just going to tell you, well, hey, look, if you let a and b both be 1, it's very simple, because when I move that up and cross multiply, it's m minus p, and then there, if that's 1, that's plus p, p's cancel, and you get exactly what we want. So this becomes 1 over p plus 1 over m minus p dp. Then to get that derivative, I just take each, or get that integral, I take each one separately. The integral of 1 over p is the ln of p. Well, what's the integral of this? That minus p, remember p is our variable, is going to make this thing be minus, but then just the log of m minus p. All right? If you're not sure why that minus sign right there comes, where it comes from, just think about taking the derivative of this. You'd get 1 over m minus p, but then the chain rule says you have to go inside, take the derivative of that. The minus would come out front and cancel. Okay, so then that's equal to kt plus c. Well, I can use my laws of logarithms here and write this now as the ln of, when I put this on top, because I'm dividing, if that's a subtraction, p over m minus p, and that's going to be equal to then just kt plus c. Well, if I take and make each of these be the exponent for e, right, we know that e to the ln thus cancel, and I wind up with p over m minus p is equal to e to the kt plus c. But if we're adding exponents, that's the same as e to the kt times e to the c. And notice I've dropped off the absolute value there. If you think about it, there's no way any exponential can give you a negative number, so it's right to drop that off. Well, what do I do with this? Well, if I take and just invert this, right, flip it upside down, because I'm trying to solve for p. I'm trying to get p by itself. And if you see, if I flip it upside down, I'll get p in the denominator, which helps. I'm going to go zigzagging backwards, come this way now. So flip that upside down, or m minus p over p is equal to then 1 over, I'm going to put e to the c out front, and then e to the kt right there, okay? Well, if I separate this, this is just a constant. So I'm going to write that as a, and then this is now in the denominators. I guess I could have done this earlier, but that's going to be minus kt. All right, because it's 1 over e to the positive kt. Okay, well, this gives us a very handy equation that we should write down. And that is that when t is 0, okay, when t equals 0, that's my initial conditions, that'll just turn to 1. And so I can solve for this constant a by just saying, what is that maximum population minus, and I'll make little knots here, for the initial population, because this is at t is equal to 0. All right, so remember that equation. Now, I'm going to take and solve this original equation then to get p by itself. All right, so I'm going to go back to the variable form. If I have m minus p, and it's a variable now again, and if I divide p into each, or separate each one of these really, m over p, then minus p over p is 1. That's going to be equal to this a times e to the minus kt. All right, again, oops, I've lost that, sorry. I'm going to go up here. You can see what I did is I just, I got away from the t equals 0 condition. P is back to being our variable. We're solving for this. And I've divided p into m and p into p, and there we go. I want to get p by itself, so I'm going to add 1 to both sides. So I get m over p is equal to a times e to the minus kt plus 1. And then I'm going to take this whole fraction and flip it upside down, because again, it's just the quick and dirty way to get p by itself. P over m then is equal to 1 over, and I'm going to put the 1 out front, 1 plus a e to the minus kt. Okay? Well, we're close. I can get p then is going to be equal, if I multiply both sides by m, cross that out, and then I wind up with my all-important equation that the population varies with time according to that maximum amount, 1 plus then our a value, that constant value, e to the minus kt. Okay? So know this, rays of sunshine emanating from this important equation here, okay? And think about it, as time goes on, this becomes larger, this becomes smaller, this disappears, and we have m over 1. That's our carrying capacity, okay? Very, very useful. So let's see if we can put this to use and solve a few simple